Thank you very much, Partha. And so I'm very thankful to Amit and Partha for inviting me to give a lecture on some geophysical applications. Well, originally I wanted to talk on complex systems, but Amit suggested that something on solitons would be valuable. So I will point out some of the interesting geophysical and in particular oceanographic applications of solitons. Especially it's of interest because these oceanographic applications are taking place around this country, India. So I'm going to mention about some of these aspects. So I'm not sure how many, what is the understanding of soliton and its consequences for this audience, but I will quickly try to go through some of the ideas. So the main theme is that soliton is a fairly counterintuitive entity, wave entity, in contrast to the standard progressive waves and wave packets and so on, which arises due to the delicate balance between dispersion and nonlinearity. So its major attraction is the localized form, structure, and localized energy, and preservation of its shape and speed, its structure and collision. So that is a remarkable structure. So as a consequence, it has great ramifications in many areas, including tsunami dynamics, hydrodynamics, and magnetism, condensed matter, etc., etc. So I will give a brief overview of solitons, in particular in connection with Quatebec-de equation, what I call as Quatebec-de equation, which is a third-order nonlinear dispersive partial differential equation, and its applications related to oceanographic problems. Okay, so that's my main motivation. So just a couple of minutes I will take for the historical introduction, because that's also very much needed, because I will make a brief mention of the derivation of Quatebec-de equation to describe what is known as basic Scott-Russell phenomena. And that is very essential if you want to understand many of the large wave applications, geophysical applications that are involved. So Quatebec-de equation, solitary waves and solitons, and related nonlinear partial differential equations, and a very brief mention of mathematical theory of solitons. But I will concentrate on the geophysical oceanographic applications mostly in my talk. Okay. So I call solitons as a counterintuitive entity because these are standard linear dispersive waves in one spatial dimension, so x, and this is the amplitude. So you have a single progressive wave and a combination of two waves. When they are added, you have troughs and increased amplitude and so on. And if you add many waves, then you have wave packet forming the outline of this wave packet. But then these are linear dispersive waves because of that, as these waves propagate, they disperse and die down once. That is the basic characteristics of linear dispersive waves. But then soliton is a remarkably stable structure. It arises because of nonlinear dispersion. As a consequence, you have what is known as basically sinusoidal waves and the limiting form solitary waves. And in certain cases, they become solitons, what I will point out as solitons. Bent solitary waves become solitons, and they become, the underlying system becomes completely integrable dynamical, a nonlinear dynamical system. And these solitons occur in very many ways. In particular, if you consider tsunamis like Chilean tsunami in 1960 or 2004 December, Indian Ocean Sumatra tsunami. It is very meaningful to consider these tsunamis are essentially very long wavelength entities and comparatively small amplitude, but propagates without change of form or speed over long distances. So such tsunamis, it's very meaningful to talk about solid as a soliton. But there are differing interpretations, but there is a large body of literature which essentially represents tsunamis as solitons and its modifications. Okay. Then we have what is known as internal solitons. We consider the waves propagating in certain structures in the Malacca Straits of Andamans. Then seafarers very often encounter choppy waters, and oil rigs, which oil companies construct there, very often undergo damages, and it has been in 1980s, 90s, and so on. People have, through satellite imaging, have identified existence of not only surface solitons, but internal solitons. So if you consider the sea water as consisting of warm upper region layers and cold lower layers, and in between the temperature difference essentially leads to what is known as internal solitons. I will point out what it is. Then Rossby solitons, which arises in the atmosphere when the planets rotate. You have layers of atmosphere which gives rise to long wavelength solitons. And then Bohr solitons, when rivers enter into open seas, estuaries, in the estuaries, when tidal waves, big tidal waves or tsunamis arise, they can propagate in the opposite direction, opposite to the flow of water, and essentially ending up in the form of solitons. Essentially. So these are all like capillary soliton again in hydrodynamic situations, optical solitons and optical fibers, magnetic solitons, topological soliton, higher dimensional solitons like plane solitons, lump solitons going off in 2+1 dimensions as algebraically to 0, and dromions exponentially falling off in 2+1 dimension, light bullets in 3+1 dimension, and so on. So there are many facets of solitons that can occur. So this was the person, John Scott Russell, in during 1800s, observed perhaps the first experimental entity which he called as solitary waves. And in particular, he obtained phenomenologically by investigating the connection between the wavelength c and the height of the waves in this particular form, c equals √G h plus k, and which is remarkably found to be exact. So this is the standard quotation, which was originally written by John Scott Russell. He was traveling on the banks of the canal connecting the cities of Glasgow and Edinburgh, and perhaps many of you are aware of this quotation, but still I will very quickly go through. And this is also very important to understand the geophysical solitons. It was observing the motion of a boat which was rapidly drawn along a narrow channel by a pair of horses. When the boat suddenly stopped, not so the mass of water in the channel which it had put in motion. It accumulated around the prow of the vessel in a state of violent agitation, then suddenly leaving it behind, rolled forward with great velocity, assuming the form of large solitary elevation, a rounded, smooth and well-defined heap of water, which continued its course along the channel, apparently without change of form or diminution of speed. Exactly these words we now use for in defining solitary waves and solitons. I followed it on horseback and overtook it still rolling on at a rate of some 8 or 9 miles an hour, preserving its original figure some 30 feet long and 1 to 1.5 feet in height. Its height gradually diminished, and after a chase of 1 or 2 miles, I lost it in the windings of the channel. Such, in the month of August 1834, was my first chance interview with the singular and beautiful phenomena, which I call the wave of translation, essentially a solitary wave. So you have water wave propagation in a shallow channel. So if you want to model such a wave. It was, in fact, after 100 years, in the same canal, it was reproduced on the 100th year anniversary of Scott Russell's observation. And so some of the soliton physicists are here observing this solitary wave. It's essentially in 1895. So originally it was observed in 1834, and two Dutch physicists, Korteweg and De Vries, have from first hydrodynamics principles deduced the appropriate equation describing such wave propagation. And they showed that Korteweg-De Vries equation indeed admits solitary waves, sinusoidal waves, solitary waves, and more interestingly, this particular form connecting velocity and depth of the wave and so on. Okay? It is a unidirectional water wave propagation in a shallow channel in one dimension, and we assume incompressibility, invisibility. Okay? So essentially you have a wave propagation. So consider this two dimension. X is the propagation direction and Y is the vertical direction. So you have a solitary wave formed. Okay? In solitary wave, you have the wave amplitude A, the maximum height of the wave, and which is represented by eta of xt. Eta of xt is the amplitude of the wave, and its maximum height is A. And you have a channel with a height h, water depth h. So you have two small parameters you can introduce into the problem. A, this wavelength, this wave height A is much lower than this height of the water on the in the channel. So A is much less than h, and h, the height of the wave, height of the water is much lower than the length of the wave, L. Okay. So these two conditions, this is shallowness condition A, very small compared to the height of the water, and H is very small compared to length. So long wave, shallow water wave propagation, you can have parameter epsilon equal to A by H, and delta is H by L. So if you introduce these two small parameters into the hydrodynamical equations, which is represented by the fluid motion represented by the velocity vector v of x, y, t, which has two components along the x direction, y direction, unit vectors I and j, with the corresponding components u, x, y, t, v, x, y, t. The water is irrotational, so you have del cross v equal to 0, which means you can define a velocity potential v equal to grad phi. So which means you have essentially del square phi equal to 0, the Laplace equation for the wave, because you have the conservation of density, d rho by dt is rho t, del dot rho b equals 0, and rho is constant, so you have the Laplace equation describing this water wave. We also have the Euler equation for the velocity, dB by dt is partial dB by dt, v dot grad v, that is equal to the gradient in the pressure P, P by rho naught. Rho is constant. So this is essentially Newton's equation for continuous fluid. Okay? Rho naught, if you bring this, rho naught dV by dt equal to force acting on the system. So divide by rho naught, so you have 1 by rho naught grade P minus the vertical force is the gravitational force acting along the y direction. So you have the unit vector J minus G. So now you substitute V equal to grad phi, then you get essentially this equation describing the velocity potential phi t of del phi square, etc. So this is the equation of motion describing inviscid incompressible fluid, okay, from the Euler's equation. But then you have to worry about the boundary conditions. So this is a very important problem. So what is the boundary condition here? So you have the bottom y equal to 0. That's fixed, and the velocity potential is 0 at the value y equal to 0. Whereas at the upper boundary, you have a free boundary condition. So you incorporate these two informations. Phi of y, velocity along the y direction, is x0 t equal to 0. And you have the wave amplitude y, the height h, plus the amplitude eta of xt. And from which, if you take the derivative dy by dt, you get phi 1y is eta t plus eta x phi 1x as a boundary condition. And at the boundary, the pressure P1 is 0. So from the Euler equation, you have U1 T, U1, U1x, V1, Vnx, G eta x equal to 0. So you have these two boundary conditions and one fixed boundary and two free boundary conditions along with the Laplace equation as the equation of motion. Now, from the standard hydrodynamic way, you make a Taylor expansion because assuming y small quantity and you have the Taylor coefficients and then substitute in the Laplace equation, compare coefficients, etc. So you have the u1 vertical, the horizontal velocity u1 is related to the first coefficient df phi naught by dx, and v1 is again related in this way, and so on. Now introduce the small parameter epsilon delta into the problem by scaling u1, v1, etc. appropriately. So you have an epsilon, you have an epsilon delta, etc. coming, and the height also you modify essentially. Then you end up with, and this approximation end up with a coupled partial differential equation, okay? A system of two coupled partial differential equation. It is nonlinear because eta fx, epsilon ffx, etc. Then from the standard way, you carry out a perturbation for this potential function f, the gradient of the potential function in the small parameter epsilon, delta, del square, etc. Then compare the coefficients, you find f0, f1, etc. And substitute in, you get this particular equation. Okay? And this is nothing but the Quatermain-De Vries equation after scale change. Suitable scale change, you get ut plus or minus 6u, ux, u triple x equal to 0. So that's what Quatermain and De Vries had done in a very short this thing. The details of all this are given in my book on nonlinear. Well, I will give in the end. All the details are given. So this equation admits sinusoidal wave. If you look for wave solutions of this form, then you can integrate this ODE and you get this Sn square f equal to Sn square. And in the limit m equal to 1, then Sn square become tan h square. And if you give appropriate values for these various quantities alpha 3, alpha 1, etc., you get sec h square. So that is the nicety of the problem. And instead of the standard sine cosine, which will be obtained when m equal to 0, but m equal to 1, you get this solitary wave. So isolated wave like this. Okay. Not only that, well, this problem, this Quatermain-De Vries equation appeared again and again in 1960s in the study of wave propagation and harmonic lattices. Again, it came. And then the main point is that this is a completely integrable system. 1960s, Norman Zabisky and Martin Kruskal at Princeton Plasma Physics Laboratory integrated this equation numerically. And so if you start with an arbitrary wave initially with periodic boundary condition, half of a sine wave, and you wait for sufficiently long time, this dotted curve comes, and if you wait for a very long time, then you find a large number. Actually, there are 9 pulses that are occurring here. And interestingly, these pulses, the larger one travel with larger velocity because you find the amplitude is c by 2, and you find the velocity is also c. The amplitude is proportional to velocity and vice versa. The larger the wave, the larger the speed, and so on. So as a consequence, you find this larger wave will overtake the smaller wave. And more interestingly, if you consider 2 such waves, this is unidirectional wave propagation. As a consequence, the propagation is to the right, and the larger one will catch up with the smaller one. There will be interaction, and surprisingly, after interaction, they separate out without change of form or diminution of speed, except for a phase shift. So that's why you call solitary wave a soliton. Okay. So solitary waves which retain its shape and speed under collision except for a phase shift which encounters elastic collision is soliton. Over the years, there has been many variations. Even in this analysis, you can deduce other kinds of equations like Boussinesq equation, Benjamin Bonner, Kamasa-Holm equation, etc., and other in 2 + 1 K-P Petviasvili equation, etc., modified KdV equation, etc. You can in other situations you have Sine-Gordon, nonlinear Schrodinger equation, Heisenberg ferromagnetic, etc. So all these equations, not only Korteweg-de Vries equation, all these equations are linearizable and completely solvable. So given the initial condition, you can associate the unknown function u because it is a nonlinear differential equation, partial differential equation. Consider the Schrodinger-like eigenvalue problem such that u vanishes efficiently fast at infinity with a time evolution for psi in this particular form. This is again a linear equation in psi where u occurs as coefficient. If you take the compatibility of these two, then you have the KdV equation. So what is the advantage? You have in the initial condition, you want to find the general solution of the nonlinear evolution equation. Instead of going directly, you don't have a procedure. You carry out a 3-step process. You carry out a direct scattering analysis from the initial data. You get the scattering data at t equal to 0, and then look at the time evolution equation. Asymptotically, it takes a very trivial form, and then you get scattering data at an arbitrary future instant and do an inverse scattering. Get by solving a system of linear Volterra type integral equations, then you get the solutions. Okay? And so the result is you have 1 soliton, 2 soliton, n soliton. If you plot these 2 soliton, you get that soliton collision and so on. There are many other interesting properties associated with soliton system. For example, if you make this substitution, you get the Korteweg-de Vries equation in this linear form. You can develop a method and obtain the soliton solution. You can obtain Becklin transformation, infinite number of conservation laws. There are interesting geometric group theoretic properties, Hamiltonian, bi-Hamiltonian structure. Essentially, these are all completely integrable, infinite dimensional nonlinear dynamical systems. So where does the application come? So consider the tsunami of 2004, December 26, etc. So you had a huge earthquake of the order of around 9 Richter in the Richter scale, or even the Chilean tsunami of 1960, it was I think around 9.8 in the Richter scale and so on. And then this, when an earthquake occurs, it essentially displaces large amount of earth. So it's a massive influence. Because of that, tsunami is formed. So how this leads to such tsunami formation is one problem. But then how it propagates, so that is the second problem. And when it enters or encounters a surface, how it behaves, inundation, etc. That's the third problem. So I am essentially concentrating on this propagation part. So when a tsunami is formed like this, wave propagating and so on, essentially you have waves of wavelength of the order of 200 kilometers typically. And the surface, the water depth in the sea, essentially between 1 and 4 kilometers. Okay, in Sumatra, essentially it's around 3 or 4 kilometers. Okay. And the water height, the wave height, is roughly from the after effect satellite imaging, it was identified around 60 centimeters, up to 1 meter, you can say. So if you substitute this, for example, epsilon equal to a by h is of the order of 10 power minus 4, and delta square is of the order of 10 power minus 4. So these two are roughly approximate. So propagation of tsunami waves can be modeled, at least these waves which propagate over long distances. You know, 2004 tsunami waves even reached Somalia, Kenya, the shores of Kenya, Somalia in Africa. So around 10,000 kilometers journey without much change in the form, shape, and speed, etc. So there is very good sense in assuming that these are essentially solitons or solitary waves. Recently, there has been a lot of interesting generalizations. For example, in Anjan Kundu's group in Saha Institute, they have introduced additional modified boundary conditions, obtained wave equations, Korteweg-de Vries equations with variable coefficients, inhomogeneity introduced, and 2 plus 1 dimensional generalizations, etc. Also they have identified and so on. Internal solitons. How much time? Yeah. Seafarers through Strait of Malacca often note that in the Andaman Sea, bands of strongly increased surface roughness occurs. These are essentially internal solitons which were observed by synthetic aperture radar images of European research satellite 1 and 2. Okay. So they are solitary wave-like distortion of the boundary layer between warm upper sea and cold lower depths. Okay. So these are essentially peculiar striations of 100-meter long, approximately, separated by 6 to 15 kilometers and grouped in packets of 4 to 8 of the surface of Andaman and Sulu of Philippines and so on. So these secondary phenomena of internal solitons. Internal solitons are essentially traveling edges of warm water with enormous energy affecting oil rigs. Okay. So why the satellite imaging, etc., were done? Because these oil companies were interested, because these oil rigs were damaged. So these are the these striations, wave packets, 1, 2, 3, 4 waves, and there is another group, 1, 2, 3, 4. So SAR image of Andaman Sea acquired by ERS2 satellite. So essentially you have surface soliton occurring, but also internal soliton. So you have two liquids, warm upper water and cold lower layer of water with density ρ1, ρ2. So because of this variation in density, you have a boundary layer. Then essentially, again, you can modify the detection of Korteweg-de Vries equation and show that you have this kind of solitary waves which can occur. And so many interesting observations were made by Osborne and group over 1980s, 90s, etc. And they have found that underwater currents by an oil rig drilling at 36,000 feet below Earth in the Andaman Sea. And even some of the rigs were twisted through 90 degrees and so on. They identified essentially KDV solitons. There are many other similar situations which have been observed over the years. And as I pointed out, there are two incompressibly immiscible fluids of density ρ1, ρ2 with depths H1 and H2, essentially leading to KDV. And more generalizations, intermediate long wavelength, Benjamin Ono, these are all generalizations of KDV equations. They describe solitons. So Rossby solitons. So in the atmosphere of a rotating planet, fluid particles, so they have their velocity, rotation rate, depending on the latitudes. Okay? As a consequence, motion in the north-south direction is inhibited, just like in the internal wave, vertical motion is inhibited because of gravity. So the motion in north-south direction is inhibited, and you have large-scale atmospheric waves caused by variation of Coriolis frequency moving in the east-west zonal flow. So KDV equation can model Rossby waves, long waves, incompressible fluid, and these have been experimentally confirmed in 8 years of TOPEX, Poseidon altimeter observations in the Pacific and so on. There are many interesting. Then Bohr solitons. So when you consider open sea and reverse propagation of river water, so tidal waves, tsunamis, storm surge hits an estuary, the hydraulic jump, stepwise perturbations like shock wave in the water height and speed, propagates in the opposite direction, upstream. Okay? And far less dangerous, but very similar to the Bohr, is the Bohr, a tidal wave which can propagate in river for considerable distances. For example, in Seine River in France, Hooghly River in the Ganges, you have seen, people have observed over many years, this Hooghly River had one 1 meter jump, discontinuity, etc. occurring. Sinai River also, it was observed, and then in 1980s, etc., due to dredging, it was lost and so on. Similarly, in 1983, Japan sea tsunami bores ascended many rivers and so on. So there are many such situations which occur. Yeah, just 2 minutes it will take. This tidal bore at the mouth of Argano River and so on. So there are many other situations where solitons occurs in physical systems. I'm not going into the details. Well, I will skip that. Just pointing out, in recent times, yet another interesting geophysical application is these rogue waves. Okay? Essentially, I mean, it can occur in shallow waters, but more interestingly in the deep waters. And these are waves which appear from nowhere and disappear suddenly. And so that means they are unstable structures, unlike solitons. But they do occur, people have observed, and they can damage many of the ships and so on. So if you consider, for example, nonlinear Schrodinger equation for deep water wave propagation or coupled nonlinear Schrodinger equation, Manakov, they admit what is known as breather solitons. And in the limiting form, you have algebraic structures which goes off very fast to zero, but both in time and space. As a consequence, they occur for a finite time and then disappear again. So such structures do occur. These are called rogue waves of various nonlinear type Schrodinger equations. And now, in recent times, in many situations, in Bose-Einstein condensates, optics, etc., that have been encountered. If you go to higher dimension, you have plane solitons, lump solitons, algebraically decaying in all directions, or dromions exponentially falling off. Whether you have localized such explicit localized solutions in 3+1 dimensions, etc., is not known. You have light bullets, but their forms, their stability, etc., are hardly questioned. So to conclude then, solitons are very stable nonlinear entities, occur in 2+1 and 1+1, 2+ dimensions, have considerable physical relevance. In particular, in geophysical context, I think they have very much relevance. But in 2+1, 3+1, they have, okay. This actually, it has appeared in 2009 and reprinted in 2013, tsunamis and other oceanographic applications. Thank you very much. Sorry, I have to rush through because it's 30 minutes.
Questions, comments, yes.
So there is a wavelength associated.
Loudly speak.
There is a wavelength associated with the solitary wave. So like
wavelength is effectively infinity, so that means it's very large.
No, the question
because it's a secant h square function. It starts from -infinity to +infinity. It's a single wave, isolated wave. That's why it's called a solitary wave.
Single wave, we start from some phase and then we go back to the same phase. Then we say this is the wavelength. But here, this is not that.
Yeah, so at left it is 0, at right it is 0. So you have essentially a single wave. So essentially of length infinity. But 200 kilometers, 500 kilometers, etc., you essentially consider as infinite.
Example you gave about this Malacca Strait and this internal.
Yeah. Yeah.
So how are you managing to perturb such deep water? Not like winds will only.
No, you consider seawater. I mean, I don't know, oceanographers, I mean, they found that you have 2 layers, the warm upper layer because of sun heating, and then cold layers. You have boundary layer, yes.
But when winds are moving and they are causing disturbances, but you are saying you get amplitude even deeper down kilometers.
Yeah. So because I said the seafarers along this Malacca Straits, they observe choppy waters of what I had shown in this particular form. So these are essentially images of this boundary layer between the upper and lower things. Okay. So physically you observe when you pass through ships that some regions you have these choppy waters, and then there is a calm sea, and then again these choppy waters, etc. So people were wondering what's happening here. And then now this analysis tells that they are essentially solitons, internal solitons. And more so, they want, I mean, people investigated this because these oil companies were drilling and using rigs. And these were very often when these internal waves contain a large amount of energy, when they pass through, these are disturbed, damaged. So they wanted to investigate why these things occur, and they've shown that as internal solitons. Which one?
Three-dimensional version.
Why 3 plus 1 dimensional KDB? Is basically, no, it's more complicated than that.
Yeah, they are very complicated
I'll show you.
structures.
I'll show you. I'll show you. Only one.
So the internal soliton is inverted in geometry.
Yeah.
So is that the argument why you invert?
Yeah, KDB equation, I mean, it's if you, that 6u, I mean, ux, that coefficient 6 is not mandatory. You can just make a small scale change. You can bring in an arbitrary constant. So it could be plus or minus or some fixed value, etc. So both positive, negative, etc. are solutions of Korteweg-de Vries equation, depending on that signs there.
So then I was looking for the physical argument why it is not double. Why it is not.
Well, as to distinguish, I have shown this. One could also encounter a soliton of the same structure as the surface B.
One can.
Yeah.
Any more questions, please? Let us give a big thanks to him.
Thank you.